Today we are here to discuss the mean value theorem, an important concept in calculus. And it has to do with smooth and continuous functions over some interval. And the theorem promises that there is a number exists that you'll be able to go to that number, find the derivative, and it will equate to the average rate of change of the function on that interval. So there are conditions that must be met. First of all, the function must be continuous, at least throughout the interval, from end to end. So this is an inclusive interval. And the function must also be differentiable on the open interval that you are exploring. And when those conditions are met, the mean value theorem says there is a number c. And there are two things that are true about the number c. Number one, you'll be able to find it somewhere in the interval a to b. That's an open interval. And if you can find it, go there and compute the derivative, and it will equal to this calculation. Of course, this calculation is the average rate. And don't worry, I'll illustrate this with lots of examples today. One of the things about the theorem that we have to know is the theorem states that something exists, and it doesn't tell you how to go and find it or whether it can be found. It just says it's there. And the thing that's promised to exist, this number c, remember, is an x number. It's in the domain of the function. And then the third thing you have to remember, like most statements in mathematics, there are conditions that have to be met. So things are stated in the form of a conditional. There's if and there's then. The if part of this statement has two conditions that have to be met. And remember, when these conditions are met, a promise is made. When these conditions are not met, then this theorem has nothing to say. It doesn't say whether this will be true or whether this will be false. Well, let's take an example. Here's the function cosine, and I'm exploring this function on the interval that goes from 0 to pi. Cosine is smooth, continuous, and decreasing throughout that interval. And our job here is to find the value c such that f prime of c equals f of pi minus f of 0 over pi minus 0. First of all, what is this calculation? Why, that's the average rate. It is, in the mean value theorem, the word mean really means average or arithmetic mean. So what is it that we're averaging? Well, I said that cosine is decreasing. Right here, the cosine's rate of change is 0. Over here, the cosine's rate of change is -1. Over here, the cosine's rate of change is some negative number, but it's closer to 0 than -1 is. And by the time you get to the end of the interval, the rate of change is back to 0. So you get lots of different negative rates of change or derivative through here. And what this calculation does is take the average of all those. It's the average rate of change. So we're going to want to know a couple things. Number one, when x is 0, what is f of x? And the answer is 1, because the cosine of 0 is 1. When x is pi, what is f of x? And the answer is -1, because at pi, the cosine is -1. Well, let's go ahead and compute that average rate. So that's f of pi minus f of 0 over pi minus 0. So that's change in y over change in x. This goes all the way back to the concept of slope that you learned in your early algebra days. Well, substituting these numbers into the numerator, I have -1, -1. And in the denominator, I have pi minus 0. And that computes to be -2 over pi. Okay, so there's been a little bit of discussion here, but remember, we want to state, in writing that we are aware that the conditions of the mean value theorem are met. So you might want to say something like, since this function f is continuous on the closed interval 0 less than or equal to x is less than or equal to pi, and this may seem a little pedantic, but we're going to do it, f is differentiable on the open interval 0 is less than x is less than pi. Okay, since those conditions are met by the MVT, and I'm abbreviating mean value theorem here, there is a number c and what's true about this number? Two things. I can tell you roughly where you can find it, and that is that c will be found between 0 and pi, and that is an open interval. So strictly between 0 and pi. And then the other thing about it is f prime of c is going to equal the average rate, which we've already computed to be negative 2 over pi. Now, if you actually want to go find this number, you have to get the derivative of cosine, which is negative sine, and you have to solve f prime of x equals negative 2 over pi. We're going to take a look at a lot of examples where the conditions are not met. So this statement says, when one or both of the mean value theorem's conditions are not satisfied, the conclusion may fail. It may fail. So let's take a look at x to the 2/3 on the interval negative 1 to 1 and find the number guaranteed by the mean value theorem, or discuss why the number does not exist. So it's important to know what x to the 2/3 looks like, and I'm just going to make a quick sketch of it to save time here. X to the 2/3 looks a little bit like the square root of x, but back here you see the same thing, sort of as a reflection over the y-axis. And quickly here, if I put negative 1 into this, I square it and get positive 1, take the cube root, and the y value here is 1. If I put positive 1 in, I get the same. So here's a function that has a value of 1 decreasing to 0, going back up to 1. The average rate of change of something that starts at 1 and ends at 1 is 0. And in fact, if you drew that secant line through here that I talked about, its slope is 0. However, we're not going to do all that because this function does not satisfy one of the conditions of the mean value theorem. This function is continuous on the closed interval negative 1 to 1, but this function is not differentiable at 0, and 0 is in the open interval negative 1 to 1. So about all you have to do for this is say f is not differentiable. That's really all you have to say. Because as soon as one of the conditions of the mean value theorem is not met, then the mean value theorem has nothing more to say. So I should use the preposition on here, meaning all the way through. And why is it not differentiable? Well, there's a graphical reason for it here. I did my best to draw this, but if you get down here, you can see that from left to right, I'm approaching an infinite slope that's negative, but going from left to right, this slope is leaving positive infinity and going to smaller positive values. There's no derivative right there. And a more analytical reason for that would be to do something like this. If f of x equals x to the 2/3, then f prime of x is 2/3 x to the negative 1/3. And trying to evaluate this at 0 would be division by 0, which we're not going to attempt. It's undefined. Okay, so you can't plug 0 into that. So there's no derivative at that point. All right, here's another example. A new function. I made this one just for you. Function g is x squared plus x minus 1 minus absolute value of x minus 1 divided by x minus 1. discuss the mean value theorem for the following intervals for this function, -1 to 0. Well, let's take a quick look at what this function looks like. It looks like this. And as you can see over here at x equals 1, there's a very large discontinuity. But that's not going to bother us between -1 and 0. As a matter of fact, as long as x is less than 1, for all values of x less than 1, this function is just a parabola that has an equation much more simple than that. So if I put a number here smaller than 1, like 0, I get -1 here, but with the absolute value, I get +1. And so dividing these makes -1, and then this takes the opposite of that to make a +1, which cancels with that. So I guess I don't want to spend too much time on this, but just make a note. For x is less than 1, g of x simplifies greatly to just being x squared plus x. Now, that is a polynomial. Polynomials are differentiable and continuous for all x values. So you might want to say something like, since g is continuous on the closed interval and also differentiable on the open interval, there is a number, and it's an x number, and this is what we know about it. Two things. One, we can find it. Well, if we can find it, it'll be between -1 and 0 strictly. So c is found in this open interval. And two, the other thing that's important is, if you evaluate the derivative at c, it should come out to be the average rate. Now the formula for the average rate for this interval is f of 0 minus f of -1 over 0 minus -1. And I think I'll refer to my calculator to get the values that I need here. Or you could certainly plug into that. That's probably just as easy. But watch. Trace to -1 and y is 0. Trace to 0 and y is 0 again. So keep that in mind. On this interval, the y values at the beginning and the end are both 0. So that ends up being 0 minus 0 over 1, which is 0. Now this is a special case of the mean value theorem where the average rate comes out to be 0. And in particular, both the y values associated with these x's are zeros themselves. You're going to hear this come up once in a while, but this special case of the mean value theorem is called Rolle's theorem. And the idea behind Rolle's theorem is, if you're studying an interval and you have a continuous differentiable function, and there are 0 values for y, in other words, at -1 and at 0, the y values are both 0, so this function has roots there, then there will be a point where the derivative equals 0. And that point will be somewhere in the open interval. Now, as far as finding that point, Rolle's theorem, mean value theorem, they don't tell us how to find it, but it's usually pretty easy. All you have to do is solve this. Solve g prime of x equals 0. Why 0? Because that's the average rate. What's g prime? Well, that's just the derivative of that. So I have 2x plus 1 equals 0. And of course, when I solve that, I get x equals -1/2. A picture's worth 1,000 words. Remember, between here and here, the average rate is 0. There's decreasing and there's increasing, but they basically balance each other out. You get an average rate of 0. Right here at x equals -1/2, there's a point where the derivative actually is 0, and that -1/2 is the number c promised by the mean value theorem. Okay, I won't say a lot about this. On the interval 0 to 1, what's going on there? Well, let's see. Trace to 0, I'm already there. Trace to 1, and this function is undefined. And there's a massive discontinuity here. And so you cannot say that you have a function that's continuous on the closed interval 0 to 1. So the mean value theorem is not going to make any kind of statement or conclusion or promises or guarantees. Why? Because G is not continuous on 0 is less than or equal to x is less than or equal to 1. And that's the end of that. So moving on. Here's an interesting little function, x squared minus 9 over x minus 3. It's a rational function. Now, rational functions are continuous and differentiable as long as they are defined. They're undefined for any x that causes division by 0, which clearly here is going to be 3. 3 minus 3 is 0. You can't divide by 0. This function becomes both discontinuous and therefore not differentiable at x equals 3. But everywhere else, it's fine. As a matter of fact, you probably learned when you studied limits, factoring and canceling is helpful. Well, go ahead and do that. X squared minus 9 is x plus 3 times x minus 3. And if you're dividing this by x minus 3, go ahead and cancel the x minus 3's. But just be careful. It's not quite correct to say that h of x is equal to x plus 3 when we know that h is undefined at 3 itself. So this is true as long as x is not equal to 3. Otherwise, the function is undefined. But on this interval, okay, this little linear polynomial is exactly equal to h of x, because we're not in an interval where 3 is going to cause a problem. So again, we have a polynomial, and so we want to write out the whole thing about since h is, and I'm going to abbreviate it this time, I'm just going to write differentiable and continuous. And for where? Well, as long as x is less than 3 or greater than 3, by the mean value theorem, there is a number. It's an x number. There's a number c such that two things are true. One, c is found in the open interval 0 to 2. So 0 is less than c is less than 2. And if you compute the derivative of this function and evaluate it at c, it will come out to be the average rate. So on this interval, the average rate is f of 2 minus f of 0 over 2 minus 0. And I just quickly plugged the 2 and the 0 into that, and I got 5 and 3 respectively. So this is 5 minus 3 over 2 minus 0, and that's equal to 1. So how do you go about finding that number? Well, this is actually kind of interesting. As long as you're in this interval, h is equal to this. So you solve h prime equal to the average rate, but see, h prime is just 1 here and 0 there, it's 1. So if you're solving 1 equals 1, that's true for all the x's between 0 and 2. And so the mean value theorem promised us one number where the derivative would equal the average rate. But if you go graph this function between 0 and 2, it looks like this. It's linear. It has a y-intercept of 3, and it has a slope of 1 everywhere you look at it, and certainly at all numbers between 0 and 2. Derivative is 1, 1, 1, 1, 1, 1, 1, and that's the average rate also. Now, What about this function on the interval 2 to 4? Well, we have a discontinuity. So we go back and say h is not continuous on 2 is less than or equal to x is less than or equal to 4. But now remember, between 2 and 4, you're still going to have lots and lots of places where the derivative is 1. And it turns out that's also the average rate for this function on this interval. So in other words, we didn't meet both of the conditions, actually, of the mean value theorem. But nevertheless, we were able to show that there's some numbers where the instantaneous rate is equal to the average rate. Okay, a function's continuous and differentiable. I'm going to skip this one, I think, because I'm running late here, and this is all about the intermediate value theorem. I'll just make a quick note about it, though. It says, does there have to be a solution to the equation f of x equals -1 in the interval 2 to 4? Well, the answer is there does have to be a solution because -1 is between 1 and -5. It's intermediate. And this function is continuous. And for the intermediate value theorem, that's all you need. You have a function that's continuous from 2 to 4. Then any number that's intermediate to f of 2, which is 1, and f of 4, which is -5. And -1 certainly is intermediate between 1 and -5. Then the intermediate value theorem says, yeah, well, then somewhere between 2 and 4, there has to be an x that would satisfy that equation. And then this last question, which refers to the table, in what interval must there be a number c such that f prime of c equals 1? Well, they don't come right out and say that 1 is an average rate. So for you to answer this question, you're going to have to find an average rate that's equal to 1. And I'm just going to go ahead and spill the beans here. From -4 to 0, of course, is a distance of 4, and from 3 to 7 is a distance of 4. So the average rate of change of this function on this interval -4 to 0 is 1, and it's continuous and differentiable. So by the mean value theorem, there must be a number c somewhere between -4 and 0 such that f prime of c equals 1. And that's how you go about that. 24 minutes seems like enough. Hope you enjoyed this. My name's Eric. Have a good day.